Mastering AWS Elasticity, the ultimate auto-scaling deep dive. We're jumping straight into a slow, deep architectural mentoring session today. We're going to unpack exactly how to mathematically eliminate capacity failure and build highly elastic, self-healing systems right in the cloud. You know, historically, capacity planning was just, well, it was a dangerous guessing game. Let's look at the Super Bowl scenario. Say you're expecting 1 million users for this massive ad campaign. In the old days, you had to physically purchase 100 servers, maybe 6 months in advance, and that creates a brutal, two-sided trap. On one hand, if only 10,000 users actually show up, you've just wasted millions of dollars on hardware sitting completely idle. Good luck explaining that bill to finance, right? On the flip side, if 5 million users show up, your site simply crashes under the load. So the auto-scaling group, or ASG, it exists to literally, mathematically eliminate this guessing game entirely.
Right, so let's define exactly what an ASG actually is. You can think of it as a logical collection of EC2 instances. They all share characteristics, and they're treated as this single unified group for fleet management and dynamic scaling. So imagine setting a baseline where you want your CPU at 50%. When a scale-out event hits, say 10,000 new users log in, the system heats up, right? It breaches that 80% CPU mark. The ASG notices this immediately and automatically boots 5 new instances to handle the load. And the best part? During a scale-in event, when the crowd leaves and your system drops back down to 10% CPU, the ASG quietly terminates those extra instances, instantly stopping the billing clock.
Exactly. Now, to really grasp the power of the ASG, we need to contrast two fundamentally different architectural paradigms. First up is vertical scaling. Think of this as the mechanic paradigm. It's kind of like taking your only delivery van off the road, which means immediate downtime, by the way, just to weld a larger cargo box onto the back of it. Eventually, you're going to hit a hard physical hardware ceiling, something like 448 vCPUs and 24 terabytes of RAM. But then we have horizontal scalability. This is the swarm paradigm. Instead of building one massive, unwieldy truck, you just add more independent computational nodes. Think of it like a whole fleet of distributed vans managed by the ASG and distributed perfectly evenly by a load balancer.
But here's a really crucial architectural note that people sometimes miss. An ASG isn't just for scaling. Like Werner Vogel's famously said, everything fails all the time. An ASG is actually your baseline for fleet management and self-healing. Let's say you've got this legacy database and you only ever want exactly one server. You can place it in an ASG with the minimum, maximum, and desired capacity all set to exactly 1. So if the underlying hardware literally catches fire at time 0, the ASG sees that the instance died, and by time step 2, it automatically resurrects a brand new one in its place just to maintain that strict desired capacity of 1.
All right, moving into Section 1, Anatomy and Sensory Inputs.
So building this CyberSwarm blueprint requires 3 core components. First, you have the blueprint itself, which is the ASG launch template. This defines exactly what to boot. We're talking the Amazon machine image, the instance type, EBS volumes, security groups, SSH key pairs, the whole shebang. Second is the arena. This is your VPC and your subnets. It defines exactly where these instances boot, ideally spreading them across multiple availability zones for real fault tolerance. And third, we have the constraints. These act like mathematical calipers for the swarm. You define the minimum, the desired, and the maximum capacity to keep your entire fleet strictly contained within your operational and financial limits.
Now, once it's built, the ASG needs sensory inputs, right? It relies heavily on Amazon CloudWatch metrics for this. CPU utilization is absolutely the most common baseline, usually targeting an average across the entire fleet. But ALB request count is also a fantastic metric for predictable web traffic, simply tracking the requests per target. And SQS queue depth? That is the ultimate metric for decoupling background workers. But I do have a quick warning here. You've got to use extreme caution if you try scaling on memory or RAM. See, memory utilization naturally goes up as an application warms up, but it usually stays elevated even when the actual live demand drops off. It just doesn't map perfectly to live workload demand.
Right, and that brings us to a really common pitfall, the health check trap. By default, an ASG uses EC2 status checks, but those only verify if the underlying hypervisor and the operating system are running. So if your app runs out of memory and crashes at the application layer, the OS is technically still up. The ASG sees a green checkmark, thinks everything is fine, and leaves the instance alone. Meanwhile, your application load balancer is just blindly routing live customer traffic right into a dead zombie node.
So the fix here is absolute. You must explicitly configure the ASG to use ELB health checks. That way, if the HTTP ping fails, the ASG knows it's a zombie node and terminates it instantly.
Okay, Section 2, Mechanics of the Swarm. Let's trace the actual timeline of a scale-out event. At time 0, we have the trigger. Let's say CPU breaches 60% for 3 consecutive minutes, right? The ASG steps in and initiates the boot of 2 new instances. But immediately we hit the lag. You see, metric-based scaling is a latent operation. It actually takes a few minutes for EC2 instances to physically boot up, warm up, join the ALB, and finally start bringing down that aggregate average CPU. And during that lag time, the alarm is still screaming. To prevent the whole system from just panicking and launching dozens of instances you don't actually need, the ASG raises a shield. We call this the cooldown period. For a set amount of time, say maybe 300 seconds, it actively ignores all new incoming alarms until the new servers can stabilize and actually absorb the traffic.
Now, when the alarm eventually clears, the ASG has to shrink the fleet to save you money. But how does it choose its victim? Well, it follows a really precise logical funnel. First, it looks at AZ rebalancing. It targets the availability zone that has the most instances, which maintains your strict architectural fault tolerance. Second, if the AZs are perfectly balanced, it hunts down instances launched from the oldest blueprint. This effectively forces a silent, continuous upgrade of your fleet over time. And finally, if there's still a tie, it puts on its accountant hat. It aligns with the billing cycle, targeting the instance that is closest to its next billing hour to maximize your absolute financial efficiency.
But wait, just terminating a busy worker node instantly? That's going to cause drop transactions and data corruption. No one wants that. The solution here is the graceful exit, using auto-scaling lifecycle hooks. This puts the terminating instance into this sort of architectural pause. While it's paused, custom scripts execute 3 really critical tasks. 1, it immediately deregisters from the ALB, so no new HTTP traffic gets routed to it. 2, it issues a NAC, or negative acknowledgement, to SQS, meaning any messages it was halfway through processing instantly become visible to healthy workers again. And 3, it safely flushes any in-memory logs like Serilog directly out to CloudWatcher S3 before physical destruction is finally allowed.
Moving right along to Section 3, Policies and Automation.
You know, the true brain of the swarm isn't managed by clicking around in a console. It's defined through infrastructure as code, like Terraform. For real enterprise provisioning, you should never manually click launch instance in a production AWS account, period. Every single EC2 instance needs to be birthed and managed by an ASG using a strict launch template. That completely eliminates configuration drift and human error. And for Tier 0 protection, think major events like Black Friday, infrastructure as code seamlessly merges your ASGs with capacity reservations. This physically locks down the hardware in the AWS data center, which entirely prevents those dreaded insufficient capacity exceptions.
So when it comes to scaling policies, target tracking is absolutely the modern standard. You can almost think of it like an architectural thermostat. It's best used for predictable metrics, like your CPU or request count. You simply define a target, let's say 50% CPU, and that's it. AWS automatically creates and manages all the underlying CloudWatch alarms and all the math required to keep the fleet exactly at that baseline. It's so smart that it even inherently understands instance warm-up times. It mathematically excludes those booting instances from the aggregate metric, so you don't get any premature scaling.
However, target tracking isn't perfect for every single scenario. For highly spiky, really volatile workloads, you need step scaling policies. Instead of waiting around for an average metric to slowly pull back down to a target, step scaling gives you these aggressive, staggered responses based directly on how severe the breach is. So if the alarm hits 60% CPU, you might configure it to just add 2 instances. But if a massive spike instantly blasts the alarm to 90% CPU, the step scaling policy just skips the gentle approach entirely and aggressively drops 10 instances right onto the battlefield to intercept the onslaught.
Now, both of those approaches are reactive. But what about proactive provisioning? Basically, scaling out before the spike even hits. You have 2 really powerful tools for this. Predictive scaling uses machine learning to analyze your historical load patterns. If it notices your traffic consistently spikes every day at noon, it'll automatically schedule the addition of instances well before noon actually happens. On the other hand, you have scheduled scaling. This is hard-coded architectural provisioning. You dictate the exact minute to scale out. For example, deploying 50 instances at 8 a.m. on Monday for a global workforce login rush, and then automatically scaling back down at 6 p.m. to save on costs.
And that brings us to our final part, Section 4, Advanced Architectural Patterns. So a major challenge is updating a live running fleet. When you update an AMI or a launch template, the ASG does not automatically go out and terminate your existing instances. To deploy the new version, you use the instance refresh feature, which automates rolling updates. And the absolutely critical safety mechanism here is called the minimum healthy percentage. Let's say you set this to 90%. The ASG will boot the version 2.0 nodes, wait patiently for them to completely pass the ALB health checks, and literally only then will it terminate the version 1.0 nodes. This guarantees absolute zero downtime availability while you deploy.
We also really need to talk about advanced capacity planning and something called the thundering herd stress test. If you set your scaling target to 90% CPU, I'm just going to say it, you will kill your application. Why? Because metric-based scaling is a latent process. It takes minutes for the alarms to trigger and the new instances to boot. If a massive traffic spike, that's the thundering herd, hits while your current fleet is already pegged at 90%, you'll immediately exhaust that remaining 10% capacity long before the new instances ever finish booting. And that leads to a total system collapse. The absolute golden rule of architecture here is to target 50 to 70% utilization. You are paying for that 30% overhead specifically to act as an impact buffer, just to absorb the herd while the cavalry arrives.
Another genuinely brilliant pattern is decoupling the workload completely using SQS queue-depth scaling. This is pretty much the ultimate asynchronous pattern. The trigger here isn't CPU at all. Instead, CloudWatch is monitoring the mathematical backlog of the SQS queue. If the queue depth exceeds your acceptable threshold, the ASG rapidly scales out a massive fleet to process the entire backlog simultaneously. And then, for cost optimization, as those workers chew through the queue, the backlog naturally drops. The very moment the queue hits empty, the ASG aggressively scales the fleet completely back down to absolute zero. You stop billing exactly when the work is done. It's beautiful.
You do have to be incredibly careful with specific configurations though, particularly around target group sizing. This is a real pro tip. The context here is that disabling cross-zone load balancing can save you massive amounts of money by avoiding those inter-AZ data transfer penalties. But there is a dangerous catch. If you disable cross-zone routing, your ASG minimum capacity must literally never drop below your AZ count. Think about it. If you're operating in 3 availability zones, your min capacity must be at least 3. If you drop it to 2, one of those AZs will have a load balancer node pointing to 0 backend instances. That creates a localized black hole, causing a completely silent outage for 33% of your users.
Finally, let's talk pure financial engineering using a mixed instances policy. You should practically never build a horizontally scaled burst fleet entirely out of expensive on-demand instances. Instead, you configure the ASG to maintain a solid 20% baseline of on-demand instances just to guarantee baseline survival. Then you fulfill that massive 80% burst capacity using spot instances. Doing that achieves a 70 to 90% financial discount. The real secret sauce here is spot fleet diversification. You configure the ASG to request multiple instance types, like C6i, C5, and M5. That way, if AWS runs out of spare C6i capacity, the ASG seamlessly falls right back to C5, keeping your background workers alive while saving you an absolute fortune.
And that brings us perfectly to the master architecture, the ultimate elastic citadel. Every single concept we just discussed ties together into this impenetrable fortress of an architecture. Your traffic flows through Route 53 DNS straight to an application load balancer that's enforcing those strict HTTP health checks. The ALB then perfectly routes that traffic across multiple availability zones right into an auto-scaling group that is actively utilizing a mixed instances policy with on-demand survival and spot diversification. And the whole swarm, it's governed algorithmically by CloudWatch target tracking policies, and it's backed by highly available Amazon RDS databases. You literally now possess the blueprint for true mathematical cloud elasticity. So the only question left for us to ask is,